So, while coming back from CERN, see my video up there, it was a pretty long flight. I mean, it's basically Europe all the way to the US. And that's hours upon hours. I also couldn't sleep. Well, I could have, I just shouldn't have slept because time zones. So I had to do something for the flight. And it was a long time, so I watched a few movies, eventually got bored, and so I did what anyone else would do. I built a computer in Minecraft. Don't click off the video just yet. It's not just about Minecraft, it's also about computing in general. Okay, feel free to click off. Before we start, just a really quick disclaimer. This is actually going to be a two-part video. One in which I cover the basics of computing, this video, and another in which I put that into Minecraft. If it all seems a little less organized, then that's because I came up with the idea of having two separate videos while editing. And the reason for that is because just the computing alone is a good 15 minutes. I don't want my videos to be more than 15 minutes, so this is just going to be basics of computing. I'll have a link in the description when I'm done with my Minecraft video, and the Minecraft video is going to cover building the actual computer in-game. This is just the basics. That's also why I have a haircut and different clothes and different lighting and all that. It's almost a week after initially recording. So let's get started. Now, there are a lot of ones and zeros. Ones and zeros are very important for computers because of binary. And so what does this have to do with computing? Well, apart from all the GIFs you find on the internet of random ones and zeros flying around in green text while someone types on a keyboard while trying to hack, it's also how computers read. They just transform all the data into its barest components and then do stuff with that. Binary is just a format of displaying values like the decimal system or the hexadecimal system. Here's 1, 2, 3, 4, 5, 10, 50, 100, 500, 1000. Got it? No? Moving on. I'm just kidding. Binary is where all the math is going to come in. So let's go back to elementary school. Our normal method of counting is the decimal system, named for 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We think 10 is a nice number because its multiples all end in 0 and all that, and if you divide, then the decimal place just gets shifted over by 1. But that would happen in any other counting system if you divide by its base. Now we call our base of numbers 10 because it's based on 10. Binary is based on 2, but we'll get more into that later. Coming back to our decimal system, let's say we have a number. If you can't see that, I apologize. Maybe this could shed some light on it. It's a terrible pun. But let's say what's ingrained in your system so deeply. Each of these digits has a different value. This one is not the same as this one. They don't mean 1 and 1. This one means 1000. How do you know? Because you've spent your entire life looking at numbers like these. This means 1. This is 10. This is 100. And this is 1000. They're all powers of our base. For example, 10 cubed, 10 squared, 10 to the power 1, 10 to the power 0. And if you go into decimals, it goes into negative exponents, but that's all fancy talk and nothing we'll need for a computer. So the digit in this place is how much each of these values are counted. The 1 here, actually this is a bad example. Let's make it a 4. That's better. Now the 1 means that there is 1 1 counted. The 7 means that there are 7 10s counted, so 70. The 0 means there are 0 100s counted, and the 4 means there are 4 1000s counted. You may think this is all basic stuff. And why are we going through this? I already learned this. I have this drilled in my head since 5th grade. Well, it's pretty important because suddenly we shift over to binary. The base 10 system has 10 digits, all the way up. The binary system only has 2 because it's based on 2. 0 and 1. And so this number would just simply not exist because these digits wouldn't mean anything. They don't exist in a binary binary system. But 0 and 1, what would a number system like that even look like? Well, I'm just pulling out random numbers, but let's say we have a number like this, 10111001. If we use the same technique we did for the base 10, working backwards this time, we can tell that this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and all the way up. Now, I'm expecting most of you don't have base 2 system memorized, so let's just convert it to decimal system because it's familiar. 2 to the power of 0 is just 1, then 2, 4, 8, 16, 32, 64, 128. And then since these are just 1 and 0 values, we don't have to multiply them really by anything. We can just say count this value or don't count this value. So for instance, this would be 128 plus 32 plus 16 plus 8 plus 1, which is 185. This number is 185 in the decimal system. As you can tell, it's an incredibly inefficient way of writing out numbers, but when transistors are so small you can fit them on a strand of hair, size doesn't really matter. So if it's a computer, it needs to compute, and it does that by doing math. Now, starting with the simplest function of math, addition. 37 plus 46. Now 7 plus 3. 7 plus 3 is 13, but of course we can't write that in one space. You have to take this 1 and carry it. And then we have 1 plus 3 plus 4. So 1 plus 3 is 4, 4 plus 4 is 8. So you get 83. Now what would that look like in binary? These are the binary values for these numbers. You can check my math if you like, or you can just trust me on it because you're lazy like that. So just doing math, 1 plus 0, 1, 1 plus 0, 1. Then we come to 1 plus 1. I mean, we know it's 2, right? But we can't do that in binary. Binary doesn't allow for 2. So instead, it loops over to 0 again, but this time it's a balance. And we read this as 10, but this means 2 in the binary system. And of course, we can't have this. We need to balance the 1. And then the exact same things happen. 1 plus 1, well that's 2, but not really. It's 1, 0. So 0, carry the 1. And then 1 plus 0 plus 0 is just 1, 1 plus 1, 0, 1. So we get 1, 0, 1, 0, 0, 1, 0. Oh, sorry. 1, 0, 1, 0, 0, 1, 1. Which, if you want to do the math on that, you'd get 64 plus 16 plus 2 plus 1. And if you add that up, that adds to 83. Same number we got for here. And so binary works. We're not used to it, but it works. So that's where like the joke of computing 11000101 comes in. I think I got that right. Did I get that right? Yeah, I got that right. Because it's like because it's normally computing 101, and 101 is just 11000101 is 101 in binary, but 101 is already looks like it's in binary, so it's like double binary. And so, oh my god, this is the worst time my neutron star. Oh! Now let's talk gates. Logic gates, specifically, are small pieces of wiring and transistors inside your computer. Transistor is just a fancy word for switch, off and on. It's basically just a lever's a big transistor. Essentially, gates take in 2 inputs and spit out 1. The inputs either have a high voltage or low voltage, meaning they have a value of 0 or 1, traditionally. And there are a lot of types of gates. You have OR gates, AND gates, NOT gates, NOT gates, ROX gates, XOR gates, ROR gates, NAND gates, NOR gates, and ANGS gates. And I might have made some of them up, but for those of you unfamiliar with computer gates, you probably didn't even notice. However, they do have these weird names for a reason. Since they both take in either an input of 0 or 1, and 2 of those inputs and spit out 1, well, they each have different functions. AND gates require both the inputs to be 1 for the output to be 1. NOT gates just flip the signal coming in. It's actually an exception. It doesn't have 2 inputs, but just 1. XOR gates are a little more complex. Basically, the inputs have to be different. 0 or 1 or 1 and 0. If they're the same, like 0 0 or 1 1, output will be 0. If they're different, like 1 0 or 0 1, output will be 1. NAND and NOR gates are just their complementary opposites. Whatever you put in an AND gate, it spits out the opposite result for a NAND gate. And same thing for OR gates. OR gates are either one input or the other input needs to be on for the output to be on. And gates also have these things called truth tables. Now, truth tables are a way of showing all possible combinations of inputs and their subsequent outputs. For AND, it's this. You can see the 0 0 outputs to 0, 1 0 and 0 1 both output to also 0, and for 1 1 it finally outputs 1. For the XOR gate, it's this. For the NOR gate, it's this, and so on. Now let's bring all the points together and think about what we need for the computer. So what do we need? Well, we needed to add 2 values and get out 1, because that's all it's going to be doing. I'm not building anything more than that, come on. So it needs to add 2 different values. What should the limit on the values be? I mean, obviously it has to have a limit. It can't just go off into infinity because I don't have the time nor patience for that. Let's say it's a 5-bit integer. Bits are just different ways of saying pieces of ones and zeros. 1 bit is either a 1 or 0 of information. 1 byte is 8 ones and zeros, so 8 bits. Let's say the numbers we're going to be adding are up to 32. 32 is 2 to the power of 5. Now, see that 5? We'll be using 5 digits. So 5 digits, and we're going to be adding 2 of them. So 5 mystery digits plus 5 mystery digits. I mean, they can be ones and zeros. So what would we get? Well, when you're adding 2 numbers, there's almost always an extra one. I mean, try with what, 186 plus 943, what does that up to? 1029, which has a 4th digit. But that's all we'll really need. I mean, it will never go more than 1 digit than the preceding 2, if that makes sense. I'll put it in a different light. Let's say they're the maximum values that 3 places can hold in the decimal system. 1998. And so it will never cross that. And the same would hold true for binary. And so it takes in 10 values and then it spits out 6. Now how would we do that? Well, we need to take this step by step, attack it like a computer. So, how do you normally add? You start with the first 2 digits. So what would we need for the first 2 digits? The thing is, the way this computer would compute is it wouldn't do all of this at once. I mean, this is all adding them up, looking at the balance, adding the balance as well as these. And so a computer can't handle that. So what I did was, this is actually binary by the way. Let's say 1 plus 1 you get, well, that would be 10 or 1 0. I store the binary in for later over here, and then we do this addition, 0 1. If this binary has gone over there, and so then this binary goes over here, 1, and then these 2 are added, and we get 1 1 0. Now that wasn't that bad with 2 digits, but with 5, it's a lot more balancing. Is that efficient? No. Could I have thought of a better way to do that? Probably. Did I want to? I'm too lazy. So we want the computer to take in 2 digits, 2 inputs, and spit out 2 outputs. The actual number that's going here, and the balance. So what would be the relationship? Well, if we draw a truth table, like previously stated in the video, if we put the 2 inputs to any random function, this is just a way of showing a gate, it should spit out 2 inputs. So using the truth table, labeling the inputs A and B and the outputs X and Y, so 0 plus 0, it would equal 0 for both of them. 1 and 0, and and 0 and 1 because they're interchangeable. What A and B mean are A plus B. Y, the letter Y would be the number that goes here, and X would be the balance. That's what I mean when I say X and Y. So Y will equal 1. Y would also equal 1 here. And there's no balance, so X equals 0 both times. And then we come to 1, 1. 1 plus 1, well, it would equal 0 and carry a 1. So Y would be 0 and X would be 1. And so there's our truth table. Because we have to use logic gates, or maybe we didn't have to, that's just what I used. And logic gates take in 2 inputs and put out 1. We need to have 1 gate for X and 1 for Y. Now the X only turns on when both of these are on. That's an AND gate. Y only turns on when both the values are different. That's an XOR gate. And if you're wondering, XOR stands for exclusive OR because it's got special little rules. So this is our design. It's going to be using 2 logic gates to spit out 2 different inputs. This is what 1 unit would look like. You've got the inputs splitting off twice, and each of them going into one of the 2 gates, and you get out 2 outputs. So that's the end of the episode. It doesn't have a strict closing because I'm terrible at closings, and this was meant to be 1 video, and I split it into a 2-part video, so it's again disorganized. The second part of the video can be found here if I'm bothered to put it up, and by the time you see this video, it might not be out yet. Just keep checking back. Remember to do that bell thing because YouTube decided to change and now you have to click the subscribe, click the bell. It'll save you a lot of trouble later when the quality of my videos go up and you actually feel a need to subscribe. But like and comment and what else do YouTubers say? Okay, see ya.